This is François Simal from ExxonMobil. Today, we will be discussing the effect of branching on the performance of non-ionic surfactants, more specifically focusing on the hydrophobic tail of the surfactants containing low to no branching. As you can also see from this title, we will be looking at new approaches such as contact angle measurements and HLD to study those effects. Here's an overview of my presentation. I will first start with a short introduction on non-ionic surfactants, explaining the typical composition and raw materials used to prepare them. Next, I will go into more details regarding the linear and semi-linear types of hydrophobe used in the industry, and will take this opportunity to introduce LAO as a feedstock for the production of semi-linear alcohols. I will then review some of the key properties of the types of surfactants investigated in this study and describe some of their main applications. Then we will discuss the results. I will describe the various types of alcohol and ethoxylates derived from them, looking first at their physicochemical properties, and will provide the results of some of their properties as surfactants. I will conclude my talk with an overall comparison between the various materials tested here. Let's briefly discuss what non-ionic surfactants are. In contrast to anionic or cationic, non-ionic surfactants are neutral species as they do not carry any charges. Those amphiphilic molecules are constituted of an hydrophilic head, which may be polyethylene oxide or polyglucosides. This hydrophilic moiety is chemically linked to an hydrophobic tail, which can be fatty alcohol, synthetic branched alcohols, fatty amine, or polypropylene oxide. In this work, we have selected polyethylene oxide as hydrophilic head and a highly linear alcohol as an hydrophobic tail. Let me now introduce the typical linear and semi-linear hydrophobic tails used in the surfactant industry. Hydrophobes with chain lengths of 10 to 15 carbons are a good compromise in terms of solubility and detergency. The first types are fully linear alcohols produced from triglycerides, which are first hydrolyzed, esterified, and finally hydrogenated to yield a mixture of C12 and C14 100% linear primary alcohols. Another approach to prepare alcohol with low branching is to perform an oxonation of a linear olefin. This process leads to a mixture of linear and monobranched primary alcohol. The ratio between the linear and monobranched depends on the type of olefins and mostly on the oxonation catalyst. Overall, the reaction described here yields more linear than branched alcohol. The type of olefins used are called linear alpha olefin. I will describe those in more details in my next slide. LAO are important feedstock for the surfactant industry, and ExxonMobil is entering into LAO. This brings us the access to feedstock we buy today, and also the ability to broaden our product offering. This will be a full range technology able to produce from butene all the way to C2024 heavy materials. We will have a capacity of approximately 350,000 tons per year out of our plant in Baytown, Texas. And part of the C12, C14 LAO will be converted by us into a semi-linear C13-15 alcohol. Let us now review some of the main properties delivered by non-ionic surfactants. Obviously, any surfactant will enable a reduction of the surface tension of a liquid, such as water. Surfactants are also commonly used to improve the wetting of aqueous solutions on hydrophobic surfaces. The addition of a surfactant will always result in the formation of foam. Depending on the end application, foaming can be either wanted or unwanted. Surfactants play also a key role in soil removal. The behavior of non-ionic surfactants in water can vary in function of their concentration and temperature, leading, under certain conditions, to gel materials, which can have an important impact for storage and handling. Finally, non-ionic surfactants should display intrinsic biodegradability under various conditions. Lower branching levels typically enable non-ionic surfactants to be readily biodegradable within a very short time frame. Let's discuss now about the results. Let's first start by reviewing the characteristics of the different alcohols investigated in this work. Three types of hydrophobes are considered. First, Exal 1315Le. This is a new semi-linear alcohol from ExxonMobil with 36% of branch material, based on 70 weight percent of C13 and 30 weight percent of C30 of C15 alcohol. Next, 100% linear alcohol based on a 70-30 C12-C14 mixture. And finally, another semi-linear alcohol containing 20% of branching and a carbon distribution ranging from C12 to C15. Note that the average carbon number is 1 carbon shorter for the 100% linear alcohol. The various alcohols have a pour point around 20 degrees C. This is a consequence of their low level of branching. Proton NMR study has revealed that the majority of the branching of this new alcohol is composed of a metal branched on the 2 position. Those alcohols have been converted into non-ionic surfactants via a standard ethoxylation process. As you can see from this table, we did target to add 7 moles of ethylene oxide to each hydrophobes. 7 moles of EO being a very common level for these types of non-ionic surfactants. Within a medium ethoxylation range, the product possesses the highest surface activity and best wetting performance. Therefore, these products are versatile surfactants used for a wide range of application. You can see that the ethoxylation level measured by high temperature GC shows a good correspondence with the targeted one, perhaps slightly lower in the case of Exal 1315Le. At room temperature, the 1214 ethoxylate appears as a viscous liquid with a pour point below 20 degrees C. All CMC values are very low, which is typical for highly linear non-ionic surfactants, with 1315 proving to be a bit more efficient and effective in reducing the surface tension. The CC values will be discussed later in the presentation. Another important surfactant characteristic is the cloud point. The cloud point is defined as the dehydration of polyoxyethylene type non-ionic surfactants. An increase in temperature causes the cleavage of the hydrogen bond between the oxygen of the ethylene oxide group and the hydrogen from the surrounding water molecules. Thus, when the temperature rises, the hydrophilic part becomes more hydrophobic. At a critical temperature, called the cloud point, the solution separates into a micellar-rich phase and a micellar-poor phase. Because the phase separation is low, the solution first becomes cloudy. As we can see from this graph, the branching level in the hydrophobe seems to impact the cloud point. Higher branching leads to lower cloud point. On this basis, having a higher degree of branching will be favorable for many types of cleaning operations performed at lower temperature, which is gaining a lot of interest these days. Let us now discuss about the performance of these surfactants. The wetting power is a very important feature for a surfactant. The wettability is typically assessed by the Drafe test. Let me show you this short video describing how this test works in practice. A standard load is attached to a cotton thread and dropped into a surfactant solution. Timing begins when the weight touches the bottom of the cylinder and ends when the string becomes slack. Time is typically expressed in seconds. 7 moles of EO gives the optimum wetting time versus a lower level of ethoxylation. From this graph, it appears that the 100% linear alcohol ethoxylate brings a faster wetting speed. As I mentioned, there are some differences in the actual ethoxylation levels. The graph below shows the same evolution of wetting as a function of the level of ethoxylation for both exalted in 15Le and the 100% linear hydrophobe. The Draves test provides wetting speed on a cotton thread. It is of interest to assess the wettability of surfactants on other materials. The contact angle is measured using the image of a fixed drop at the points of intersection between a drop contour and the projection of the surface. The improved wettability is usually quantified as a degrees of the contact angle of the droplet on the surface. The change in contact angle with respect to time is particularly important. This time dependency reflects the speed with which surfactants absorb at the interface between the liquid and the solid. We have performed contact angle measurements on the 3 non-ionic surfactants diluted in water. In contrast to the Draves test, this approach allows us to test the wettability on different types of substrates, like glass as a polar surface, to non-polar surfaces such as polyethylene and Teflon. Interestingly enough, pure water will show this behavior on glass, high contact angle and very little changes in the angle as a function of time. The addition of non-ionic surfactants creates a clear reduction of the initial contact angle, and the spreading of the droplet is now a dynamic phenomenon. As can be seen, a very efficient and fast spreading occurs on glass, but also on polyethylene. The case of Teflon is different. Now the surface energy is lower than the surface tension of the surfactant solution. In this case, the initial contact angle is much higher and the spreading of the droplet is not evolving as a function of time. Foaming is an important characteristic for surfactants. Foaming level can be measured with a dynamic foam analyzer, such as the one shown here. 1 gram of surfactant is added per liter of water. The solution is added into the cylinder, and foaming is generated from the bottom through air sparging. This equipment provides the maximum foam height as well as the stability of the foam as a function of time. From this graph, it can be seen that the maximum foam level is slightly lower with the 1315 Le ethoxylate, which is in line with the higher branching level in the hydrophobe. In terms of foam stability, we can observe that those 3 surfactants show a comparable profile. Non-ionic surfactants spontaneously self-associate in water. Depending on their concentration and temperature, they typically yield complex patterns of phase behavior, which may cause gelling of the surfactant solution. Gelling can be detrimental, as it may cause dispensing issues or clogging. The surfactants were diluted in water from 90% concentration to 10%. Gel phases are mainly observed between 70 to 30% concentration. The aspect of the surfactants in water solution at 40 and 60% concentration are depicted in this slide and indicate that the 13, 15, 7 mole with 7 moles of EO gives the lowest viscosity. Hydrophilic lipophilic balance, HLB, has limitations. It cannot address the effect of branching in the hydrophobes. The HLD is a dimensionless expression of the difference of affinity of the surfactant for the water and the oil phase. The HLD shifts between negative to positive values corresponds to the transition between type 1, oil in water emulsion, to type 2, water in oil emulsion. HLT equals 0 means a perfect balance of the surfactants interactions with oil and water, leading to minimal interfacial tension between oil and water. This is the general equation of HLD, which is a semi-empirical relation in which the contributions of the oil and the temperature, the salinity, and the nature of the surfactant sum up. One of the key terms is the CC, which stands for critical curvature. This term is related to the nature of the surfactant. At HLD equals 0, the CC values can be calculated. A positive CC value indicates a more hydrophobic surfactants, favoring positive HLD. The phase inversion temperature of a non-ionic surfactant is the temperature at which their solubility changes from water-soluble to oil-soluble, HLD going from a negative to positive value. In this work, we have obtained phase inversion temperature through the use of dynamic methods, measuring different viscosity as a function of temperature. For a fixed surfactant concentration, a selected oil, here decane, and different salinity, the phase inversion temperature have been determined. Temperature scans of the different surfactants tested have been run with different oil under different salinity levels. On this basis, CC could be determined, showing a more positive value for hexal 1315 Le ethoxylate, indicating a more hydrophobic character for the non-ionic surfactant derived from this hydrophobe. Let's summarize the key properties in this spider graph. Taking the 100% linear alcohol ethoxylate as the reference and normalizing for the other two surfactants. In this manner, improvements are directed towards the center of the graph. Let's look at it in a clockwise fashion. The surface tension and foaming values are comparable. The more positive CC and the lower cloud point obtained with 1315 Le ethoxylate highlight the greater hydrophobicity of the ethoxylate derivative. Lower contact angle and faster spreading are also observed for the surfactants, which may also be related to its higher branching degree as well as the position and type of branch. Overall, we can conclude that those three surfactants remain fairly comparable. Finally, it is also worth mentioning that hexal 1315 Le alcohol as well as its ethoxylate derivatives are readily biodegradable according to OECD 301F and B, meeting the 10 days window. Let me now conclude. From this work, it appears that the presence of slight branching in the two positions seems to improve the hydrophobic nature of the surfactant, leading to lower cloud point, lower contact angle, and more positive CC values. In terms of potential benefits, the hexal 1315 Le allows non-ionic surfactants to be more efficient, more effective, and easy to integrate into existing formulations and manufacturing processes. With that, I would like to thank you for your attention.